Welcome to this VLSI Design lecture series. In today's lecture video, I'll be discussing about design for testability, and especially we will be covering a topic called as scan design and built-in self-test. Normally, design for testability is categorized into three testings or three approaches: ad hoc testing, scan-based approaches, and built-in self-test. So in this particular lecture video, our main focus will be on scan design and built-in self-test. The scan design strategy for testing has evolved to provide observability and controllability at each register level. So these flip-flops are nothing but registers. In designs with scan, the registers operate in one of the two modes. It will operate under two different modes. The first one is called as normal mode, and the second one is called as scan mode. In normal mode, this entire design behaves as expected. But in scan mode, they are connected to form a giant shift register called as scan chain. We can observe here, big scan chain is formed over here, which consists of scan in as well as scan out. In scan mode, as I told you, it is connected to form a giant shift register, which is called as scan chain. By applying n number of clock signals or n number of clock pulses in scan mode, all the n bits of state in the system can be shifted out and new n bits of the state can be shifted in. We can observe scan in as well as scan out. So by applying more number of clock pulses, the data will be transferred, n number of data will be scanned out as well as n number of data will be scanned in as well. Therefore, this particular scan mode gives easy observability and controllability of every register in the system. This particular figure which you can see here is nothing but scan-based testing, modern scan-based testing of registers. Here we have considered D flip-flop. The scan register which we have considered is D flip-flop, which is preceded by a multiplexer. As we already know what is meant by this multiplexer, what exactly it functions. This multiplexer has two inputs and there is a select line called as scan. So depending upon the scan input or the select line input called as scan, whether D input should be given to the flip-flop or S1 should be given to the flip-flop will be decided. When the scan signal is deasserted or when the scan signal is removed, the register behaves as a conventional D flip-flop because D input will be given. Whereas when scan is asserted or scan is triggered, S1 pin will be given to the flip-flop and the scan design process starts. For the circuit to load the scan chain, scan is asserted and the clock is pulsed many number of times. Test generation for this particular type of test architecture is highly automated. The prime disadvantage of this particular design is the area and delay impact and extra multiplexer which we are using here. In this particular scheme, each and every input to the combinational block can be controlled and every output can be observed. In addition, running a random pattern of logic level high and logic level 0 is also possible. And hence, this kind of design is widely used. In addition to the scan-based technique, we have something called as BIST, built-in self-test. The combination of signature analysis and scan technique creates a structure called as built-in self-test. So the figure which you can observe over here is nothing but built-in self-test. There are two parts in this particular figure if you observe, figure A and figure B. This figure A shows us the 3-bit register, and figure B shows us how it is used in our system. And same way in figure B, if you can observe on the right hand side, we have different modes of operation of built-in self-test. We have something called as scan mode, we have something called as test, reset, and normal mode. And it depends how C0 and C1 is given. We can understand it in a detailed manner with the help of this modes. For example, if we consider C0 is 0 and C1 is 1, then this entire diagram, this entire figure, whatever we see, becomes under scan mode. If C0 is 0 and C1 is, C0 is 1 and C1 is 0, C0 is 1 and C1 is 0, it acts under test mode. When C0 is 0 and C1 is 1, it acts under reset mode. When both C0 and C1 are high, it acts under normal condition. So this C0 and C1 specifies the mode of operation. For example, in the reset mode, when C0 is 0 and C1 is 1, it acts under reset mode. All the flip-flops are synchronously initialized to logic level 0, because under reset condition, we already know that the flip-flops, the inputs will become equal to 0. Flip-flop will be reset to 0, initial value. For example, if we consider C0 is 1 as well as C1 is also 1, then this circuit, whatever we have considered, acts under normal mode. In normal mode, all the flip-flops behave normally with the D input as well as Q output. Similarly, if we consider C0 as 0 and C1 as 0, both C0 and C1 as 0 and 0, this circuit acts under scan mode. So in scan mode, the flip-flops are configured as a 3-bit shift register between S1 and S0, between S1 and S0. Similarly, we have one more mode called as test mode. So in test mode, C0 is 1 and C1 is 0. The register here behaves as a pseudo-random sequence generator, or we can also call it as signature analyzer. In test mode, as I already told you, in all our previous lecture videos, we have discussed about this. In test mode, it will be giving us test cases, zeros and ones. It will be randomly generating zeros and ones. So when C0 is at 1 and C1 is at 0, this entire circuit acts under test mode. It starts to give out random sequences. If all the D inputs are held low, the Q outputs loops through a pseudo random bit sequence. We have a loop as well here. In summary, what exactly is meant by built-in self-test is, this built-in self-test is performed by first resetting the syndrome in the output register. Syndrome is nothing but fault. Then both the registers are placed in the test mode to produce pseudo-random inputs and identify the fault or identify the syndrome. Finally, the fault is shifted out through the scan chain. I hope that you have understood this video lecture. Thank you.